Welcome back to ECE 501B. Have to remember which class I am in. Advanced Linear Systems Theory. I think you know that the Passport assignment is there. You maybe haven't yet seen the homework assignment. I haven't yet posted that, but it is already due. What I need to find from you is I did not do my homework, and there are two editions that might be in play of the textbook, the yellow book. It's maybe no longer even yellow in the third edition. I think I will create a quiz on D2L and have you tell me, are you using or are you referring to the second edition or the third edition, and I'll figure out how I want to do the homework problems. I may have to, I haven't decided yet how I will assign those. Whether they will be coming from the third edition or the second edition, irrespective of which one, I will make those problems available to you, the problem statements. But I think the two editions of the book are close enough, and with that caveat, my notation right now, maybe I will switch it later in the semester, but right now it's relative to edition 2, the second edition, these numbers. But I think you will be able to, it will be clear from context what I'm referring to in the third edition. That's what I'm hoping. If I'm referring to Proposition 1.2, maybe that's Proposition 112 or something in the third edition. But I think you'll be able to follow just from the verbiage or the words in that particular proposition or comment or equation what I'm referring to. Today what I want to do is review vector spaces, and that basically is something with three things. It's a set with two operations where the operations are vector addition and scalar multiplication, and I will go through some examples, a lot of examples, and I'll scroll through some of those rather quickly because I think you can intuitively understand what I'm referring to on many of the examples, and then we'll slow down a little bit. We'll talk about some vector space properties. We will discuss types of proofs that might appear throughout this course, and those are actually in the inside cover of the third text that is an optional text if you wanted sort of a concise way of referring to some of these proofs and their techniques. Then, if we have time, we will define and discuss subspaces, which are somewhat like subsets, but they're not subsets. They're actually vector spaces themselves within a vector space. But now, what are these subspaces? We will worry about how do we combine these subspaces, and we probably won't be doing set operations like union and intersection, but instead we'll be doing sums of subspaces, vector space sums. And then what do we mean by vector space direct sums? And that's really in terms of, if you're still thinking in terms of sets, it's like you have sets that aren't intersecting except maybe at the origin, and that yet they fill the entire space. That's what we'll be referring to as these direct sums, as a way of thinking about those particular concepts. Here is our vector space. This is a recap, and you may not have time. I may scroll through this at 30 frames a second so that it seems like a movie. Well, I don't think I'm going to be scrolling that quickly, but you may not have a chance to copy everything down, but I think you can go back or refer to the appropriate locations in the text, and we'll slow down in a minute. But this just recaps what we talked about last time. These vector spaces are a set, and they possess two operations, and those operations are binary. They work on two objects in that set. The first one is vector addition. You now have two vectors from your set that you're combining. The scalar multiplication, you're taking an object from the field that is underlying your vector space, and then you're taking an object from your set and scaling that.
By object, do you mean it could be another vector, or clarification on what object? Is this not
So now the question is, what do I mean by object? And I want to keep that object as general as possible. That could be, I'm wanting us to think maybe in terms of things other than just always referring to a column of numbers, but it's an object is what I'm referring to is whatever it is, these elements in the set. If you now have a set, and that could be functions, it could be vectors, it could be other items or elements in the set. I'm trying to not use objects in my definition or description of object. But an object can be anything fairly general, but that is what is sitting there in this set that we now are combining or using to define our vector space. That's what I'm meaning by an object in the left cloud. In the right cloud, the object is the scalar from our field of numbers, which typically in this class will be the real numbers or the complex numbers. The object there, so we're combining two objects. In the left cloud, the objects are elements in the set. In the right cloud, the two objects, one is from the scalar field and the other one is an object from the set. So I'm using object in sort of to refer to two different things, depending on which cloud we are in or which bubble we are in. So I think it will become a little bit more clear, but I'm using it, maybe I should say a scalar object in the right-hand cloud, and in the other one it's just an object from our set. Let's look at or think about some examples of vector space. The first one that you can always sort of hang your hat on, did anyone wear a hat today? Maybe not. Didn't know who wears a hat nowadays, but we all do maybe when we're outside. The real number line, that's a vector space. You can add two objects from the real line. You can pick a number from the real line and use that as your scalar. Now your objects are all scalars, but some of those we refer to as vectors. Those are the real numbers on the real line, and then some of those we refer to as scalars coming from the real line. I'm trying to confuse you. That's the whole point. No. Here's a disclaimer. When you're thinking about a vector space, remember to think of it like a collection in which any linear combination makes sense, and not necessarily like a collection of real numbers in a column. When we think of vectors, a lot of times we think of this arrow in two-dimensional space or this line in a three-dimensional geometry, but vector can be generalized. It doesn't have to be a column of numbers. The vector might be a function, a real function. It might be a matrix. We're using a generalized, we're using a general form of the word vector. So vector is not, but then I even make a disclaimer on the disclaimer in the last sentence. Although a lot of times it's nice to still have that concept of a column of reals in the back of your head. That was just from example 1. Example 2. Well, let me scroll through these one at a time. R to the n. It's easy to visualize two dimensionals. R to the 2. R3 is a three-dimensional space. R4, maybe we can't visually see that geometrically, but we can apply the same algebraic manipulations that we know how to do from R2 and R3. And now we can go into R8, for example. Maybe we have, and in this case, what is our vector space? It is just what I said to quit thinking about in the disclaimer. This is now this column of reals. And it may be 8 tall, 8 rows tall, if little n was 8. Little n was 12, we now have 12 rows in this tall, thin column. That's R to the n. That's a vector space because you can add those vectors. You can scale them with a real number. And now if we extend that to an n-dimensional vector, maybe it's 12 tall again for the example 3, but now each of those elements in the rows of that 12 row tall vector are complex numbers. And the scalars can also be from the complex numbers. But you can now combine by adding two vectors that have complex elements. You can scale a vector with a complex number, and that forms a vector space. Vector space 3. These first 3 examples have come directly from the disclaimer. These are these columns of numbers. And I'll try to get away from that a little bit. Here, example 4, our vector space are matrices that are m rows tall and n, as in Nebraska, columns wide. And each matrix that's Michigan by Nebraska, m by n, is a vector. That's a vector in our vector space. And you can add those vectors together, element-wise. And you can scale those vectors with a scalar. Our scalar field is the complex numbers. And we can now pick a complex number and scale these matrices that are m by n. And now this is a slightly different vector space, but do you see if you concatenated these columns or rows into one column, you're now back to an m times n tall, thin vector, if that's what you want to think about. And you could add those vectors and you would get exactly the same if you would somehow unconcatenate those and put those back into a matrix. And if you scaled it, it would do the same thing. So there's what I'm saying relative to the vector concept. We're generalizing this term or word vector to encompass more than just a column of numbers. Those matrices are the elements in our set. So our set is this collection of matrices that are Michigan by Nebraska, Michigan rows tall, Nebraska columns wide. Those are all in the set, and an element or an object from that set is one of those matrices. Let's just take this and extend it. We could have infinite sequences that form a vector space, where each of the coordinates in that infinite sequence, z sub 1, z sub 2, z sub 3, and they don't have to be in numerical order. Z sub 1 could be 10. There it doesn't have an imaginary component, but it's a complex number. And maybe z sub 2 is minus I. Z sub 3 is 4 plus j7 or I7. And you just have an infinite number of those, but you can add those element-wise, and you can scale those by a scalar from the complex numbers. That's a vector space. It satisfies all of the properties of a vector space, which we will talk about in a minute. Here's one that's a little different. Here, a vector space V is this collection or set of continuous real-valued functions defined on an interval. Let's just now make it a real interval from A to B, and it's a closed interval. Now you can think of continuous functions where the horizontal axis is t, and you now have a continuous mapping in that interval, that closed interval from A to B. And all functions make up that set, and that set is now our vector space. You can add those functions, and you can scale those functions. Those functions allow two operations to exist on them. Those were continuous. You could make that even more general and say, let's just have real valued functions. They're no longer continuous. So now they could have kinks and bends in them, although my example doesn't illustrate that, or my drawing doesn't. But now I might refer to that in two different ways. I might say the vector space V is the set of functions f such that f of x ends up giving you a real when x is coming from the real line. Or I might just say the vector space V is the set of functions f that take the reals into the reals, with that description in curly brackets. And that just is this set of real valued functions f. You could sum f of x and g of x. You could scale f of x. You could scale g of x. This vector space includes all functions that map the real numbers back into the real line. And that's a vector space. So we've had real functions, we've had continuous functions. Now you could have functions that are n times differentiable or continuous when the derivatives are continuous after you differentiate n times, c to the n, on, let's say, a closed interval AB. The set of all real valued functions f, for which f itself, its first derivative, it's up to its nth derivative, those derivatives exist and they're continuous on that closed interval. That also is a vector space. Is this vector space in example 8 bigger? Well, maybe you can't, maybe we shouldn't be comparing. But this one is contained within, maybe I shouldn't say bigger, this one, correct? This is, if this was, well, maybe I should go back and say this one. This is where f and f prime are no, this is when f is continuous. This is when not only f, but f prime, f to the n are all continuous. So example 8 is a subset of example 6. This one contains fewer functions than whatever it was, example 6. This one has more functions because you don't have to worry about their first derivative, second derivative, nth derivative being continuous. So c to the n is the collection of functions f which have continuous first derivatives, second derivatives, and nth derivatives. The n plus 1 derivative may not be continuous. We aren't finished, but we will slow down. So now let's go through some other examples of vector spaces. I think now we're on example 9. Set of all polynomials. And this in the second edition, so now I'm going to have to qualify this. Page 10 of the second edition. It may or may not be on that page in the third edition, but now the notation will be P of f is equal to a constant a sub 0 plus a constant a1 times z plus a constant a, or a scalar a sub 2 times z squared, and that can just keep going, such that all of these scalars, a sub 0, a1, a2, etc., are an element of the field, and z belongs to the field. That we could say is the definition of the set of all polynomials. That forms a vector space. Example 10 is now a subset of that. Let's say that this now is the set of second-order polynomials over the real numbers. And now we're specializing f to be r, not r or c. Meaning now we put in a subscript on that p, script p, and now f, we're specializing that or restricting that to the r, the real numbers. This is now the set of a sub 0 plus a1z, or let me change that just so that we know that I've now changed this. Let's say x plus a sub 2x squared, such that a sub 0, a1, and a2, as well as x, all of those are real numbers. That's a vector space. V are these second-order polynomials. You can add those, and you can scale those. You can also think of this as the last sentence in the disclaimer. Essentially, you could now say that you can think of p sub 2 of r like r3, where now this polynomial p of x is a sub 0 plus a1x plus a sub 2 x squared. You can now say that that corresponds to this column of numbers, a sub 0, a1, and a sub 2. You could now view these second-order polynomials as a 3 vector in R3. And you can now add those coefficients, and now you would get the sum of 2 vectors. You can scale those coefficients, and you would get a scaled polynomial. That was example 10. Example 11. These just keep going and going, don't they? These vector spaces, but I'm trying to get you thinking about non-vector type of vector spaces. Example 11. The vector space of 2 by 2 matrices. Where now we have A, B, C, D, such that A, B, C, and D are all real numbers. And I think that you can see that this also corresponds to or is the same as R4, where now R4 is A, B, C, D, and that's equivalent to this vector space where the vectors are 2 by 2 matrices. That's consistent with a vector that's 4 by 1. Suppose now we look at example 12, where our vector space V is now a function f such that it takes the natural numbers, the counting numbers, into the reals. How about some examples? Suppose that suppose somebody said, let's let f sub 1, one of the f's, and we'll just give it a subscript sub 1, f sub 1 of n, let's say that that is n plus 1. That takes n, a number from the reals, I'm sorry, from the natural numbers, and maps into the real numbers. What about if we said f sub 2 of n is equal to 2n squared minus n? That takes the natural numbers and maps those into the real numbers. And we can, if this is actually a vector space, we know that their sum belongs to the same set. Where now we could just say, oh, we know that the sum, and I'll just say that's f of n, is also in the vector space. This now becomes n plus 1 plus 2n squared minus n, or this is now 2n squared plus 1. And that could be thought of analogously with that f of n. You could now view that as an infinite sequence of numbers, of reals. Meaning if you now had n and f of n, every vector, every f in that set, in that vector space, you could now have a correspondence with this infinite sequence of reals, where now you just start with 0, 1, 2, 3, and you say, okay, what is f of n when n is equal to 0? This is a tough challenge, but it's getting late in the afternoon, right? So now we plug in 1, and we get 3. 2, we get 9. 3, 19. 4, 1 more than 32, right? Do you see that we could generate this infinite? So this now, and this just goes on and on. This corresponds to 1, 3, 9, 19, 33, etc. And you could build this same infinite column for f sub 1, f sub 2, and any f that takes the natural numbers into the reals. Can you give me other examples of vectors in this vector space? Let's say an f sub 3 of n. So now you could, so f sub 3 of n, let's say others. You said a polynomial of n. What if I said 2.7n? Is that okay? That's fine, isn't it? It didn't have to give us natural numbers out, does it? It just needs to map to the reals. What about that's true? Is that okay? Do you get the idea? This is a very rich vector space. And the vectors, the objects in this vector space are, my vectors are these f's, and I have really sort of two operations. I have vector addition. You could add all of these together, but I also have scalar multiplication. And the scalars now are coming from where? They're coming from the reals. Is that clear? So if I really abuse my notation like I was before, I could think of the scalar being a scalar object and the vectors as being an object, but those vectors are from my set of objects or vectors that are making up this vector space. One more. We could say, here's example 13, and we could say a vector space W is now the set of functions f such that it maps R into R, but I'm also putting another constraint on that with this vertical line. That vertical line is saying such that, so I have functions that take the reals into the reals such that the second derivative of f, let's say with respect to x, plus the function has to equal 0. So that now I have restrictions on the functions in this vector space. But those functions now have to be such that their second derivative, when added to themselves, give us 0. And I think some of you have already identified one such vector in that vector space. You could say is A cosine of x plus B sine of x. And now if that's true, you could say, well, if that's, what does that particular f of x correspond to? If you now said, let's just make that the vector space, A cosine x plus B sine x, they have that structure, and my flexibility or my freedom are the A's and the B's. Now I could say that corresponds to AB. That particular function, not the whole vector space necessarily, but we could say f such that f of x is equal to A cosine x plus B sine x, and now with that restriction we could say that corresponds to this 2 vector made up of the coefficients weighting sine and cosine. Those are all examples of vector spaces. Let's look at what the vector space properties are. Again, relative to the second edition, this is on page 11 and 12, and they're labeled as 1.2, etc., as propositions. Every vector space V has a unique additive identity. And it really is a generalization of a zero element. It doesn't have to be an exact zero. It could just be something, depending on how you define your addition and scalar multiplication. Maybe this additive identity or this zero element is something else, this additive identity. It's some object that belongs to your vector space, which when added, however you've defined added, just gives you back the original vector that you added it to. That's yes. I can, I'm trying to decide if I want to make that a homework assignment. So I might put that into a homework assignment. But now can you think of, well, for example, let's say that you had V as a vector space that was maybe X such that X is positive and X is real. Now, what if you said the following? What if you said that the addition property is now you take X, let's say X plus Y, and now I'm going to make that something different because let's just say that this is now X times Y. And let's say that the scalar multiplication, if you had a scalar C, now if you said C times X is maybe X to the C. So now we're sort of doing something a little different. Now we're exponentiating for our scalar multiplication, and for our addition, we're actually forming a product. And now you might be asked, what is the additive identity such that when you take X plus the zero element, the additive identity, which is X times something, gets you back to X. So Y now has to be, the additive identity needs to be 1. It's not the zero element. Well, the zero element is 1. It's not a 0. Is that making sense? You see how these vector spaces can be very general and not just these tall, thin columns? How about proposition 1.3? So we haven't yet gotten there, have we? So, but if you now, well, what are you, so we need an additive identity. We need every element in V for 1.3 has a unique additive inverse. This is maybe what you were thinking. what when added to x will give us the 0 element, 1 over x. So now we have, for that earlier vector space that we used to illustrate that we didn't have to have the 0 element being the scalar 0. Okay, so that's now proposition 1.3, is every element in V has a unique additive inverse. 1.4 proposition says that 0V is equal to 0, and this gets back to the overuse of the 0. For every vector in the vector space, if we scale that vector with the 0 element, what do we get? The 0 vector, right? It's not the 0 scale, it's not a scalar 0. So in this case, we're overusing this 0. Here, it's our scalar. That's the 0 element. And here on the right-hand side, it's a vector. Proposition 1.5. A scalar, times 0 is equal to 0. So the question is, what is V? V is a vector. So whatever your vectors are in your vector space, that's V. If V is a function, if V is a column, now whatever V is, the right-hand 0 needs to be compatible with it. Okay, it's the 0 vector. So if V was a function, then the right-hand side would be a 0 function. Question? So now this particular scalar is whatever you need, which is going to give you the 0 vector in your vector space.
So if we are referring to the example that you previously explained, that the new type of the addition, if we consider that that 0 element, then I can say that additive identity is the 0 element. Then the latest property that you put in that the RHS is the additive identity.
So now what you want the additive identity.
So can we say that if the scalar 0 is multiplied with the vector V, then we get an additive identity?
So the question is, the 0 on the right, is that our additive identity? I think what I want to say is it's the 0 vector. And if the 0 vector happens to be the additive identity, then it's consistent. Okay? But I don't want to...
Yeah, but the previous example you gave, but then there 0 vector is not additive, like additive identity.
So now what here you have in this case, you have a scalar. You're scaling, you're doing the multiplication. So now you're really doing this second operation. You're doing the scalar multiplication of the 0 with your vector, and now you want that to give you the 0 vector in your vector space. Okay? So now in proposition 5, 1.5, I have A, which is a scalar, times 0 equal to 0, and this is for every A in our field. And what are the zeros here? Scalars, vectors. Is one a scalar? Is one a vector? These are both vectors, aren't they, in this particular proposition? A is a scalar. And finally, these are all properties of vector spaces. 1.6 is now minus 1 times v is equal to minus v. Here is your additive inverse. If you scale it by minus 1, then you get the additive inverse. Let's now talk about, so those are the properties of a vector space, or propositions. We haven't, so now 1.6, I'll have to go back and think about that to see how that applies to the, okay, so now maybe our scalars are, I didn't define really what they live in. If those are actually reals, well, if we look at the, yes, so this C, I didn't tell you what C is here. C can be the reals. So if C is minus 1, this gives me x to the minus 1, which is my additive inverse for that example. Is that clear? So if you say C is minus 1, now you have x to the minus 1. This is 1 over x. That now gives you the additive inverse of x, because now you take x and minus x, where minus x is 1 over x. With that definition of addition, is your head spinning yet? So that now gives us back what we want. Okay? That takes us to the 0 vector. Now, let's change gears a little bit and talk about some proof techniques, because we may want to demonstrate or do some proofs on those propositions. And this, you could then see the inside cover or covers of the third text of the course. I'll see what I can do on that, if I can scan that. So the question was, can I make those inside covers available? And I think I can do that with without getting into copyright issues. Okay, that's what I'll just make sure is okay. Theorem. A theorem is usually, or can be thought of like, you have a statement So now I'm thinking in the most general way. A statement yields a statement. Maybe I shouldn't have put that S on there. So a statement yields a statement, or you have some hypothesis yields a, let's say, a conclusion. Or you could say a statement A implies a statement B. These are all ways of cataloging theorems. Or you could say if statement A, then statement B, where if A is true, then B is true. That could be a theorem. Now, if you have these theorems, what are some ways that you can prove those theorems are actually true? And that's what I want to just quickly present. Proof techniques. Direct proof, meaning you start with this hypothesis, or you start with statement A, and you progress to showing statement B is true. That's a direct proof. You start with a hypothesis and you work your way to the conclusion. But in that process, you may actually want to start at the back, start with B and see if you can work your way to A and see if you can eventually meet in the middle, and then you can put it all together and go from A to B. You may want to work from ends AB. Or you could think of this as a forward backward strategy for proving. So that would be the direct approach to a proof, and that's usually the first thing you sort of think about. Another proof technique is proof by contradiction. In this technique, again, you have A implies B, or starting with a hypothesis, you reach a conclusion. With the contradiction, or the proof strategy for using contradiction, you start with A, and the negative of the end, the negative of the conclusion, you start with the hypothesis and the negative of the conclusion, and you try to derive a contradiction. Start with A and not B, and try to derive a contradiction or a false statement. That's proof by contradiction. We could also do a proof by contrapositive. That then works a little differently. That says you take the negative of your conclusion, or not B, and you show that that implies the negative of your hypothesis, or not A. To do that proof, you assume not B, and you progress to show not A. That one maybe takes a little getting used to, contrapositive, but it can be a nice technique. And sometimes in terms of why is this true, I like to just sort of look at the truth tables for the two different implications and show that the truth tables line up for A implies B and not B implies not A. Meaning, if we started with A and B, then A could be true and B could be true. or A could be true and B could be false, or A could be false and B could be true, or they could both be false. Then if we looked at A implies B, what can we conclude from A implies B with these four possibilities? If A is true and B is true, that's okay, isn't it? That's true. If A is true implies B is false, that's false, isn't it? So A implies B is false if A, B false. If A is true and B is false. But what about if A is false? It doesn't matter, does it? Then the truth table says that it doesn't matter what B is. So now you can't conclude anything if A is false. You can't say if A then B. Now you're not starting with A. A is now false. So you can't make the implication if A then B. It just ends up being true. So now if your hypothesis is false, then it doesn't matter what the conclusion is. It's always going to be true in terms of you can't, how do I want to say, you can't say anything about the properties of B, the conclusion. So it's like, I guess, a don't care in digital logic, but that don't care is really ending up being true. So we can talk about that a little bit offline, but if you now said, what about not B? That's now false, true, true. And not A is false, false, true, true. And what is not B implies not A. If we use the same logic that we just used to say A implies B, what does not B imply not A? If B is false, we can always say true, right? Because it doesn't, we're starting with a false premise, so it doesn't really matter the end. It's just going to be a true statement. What about if not B is true, gives us not A false? That's the wrong result. But true, true is true. And now if you compare those two columns, you have the same truth table behavior for A implies B as you do for not B implies not A. And that's why you can use the contrapositive to talk about or to conclude if A then B. It's equivalent to if not B implies not A. And so you could sort of view that as if it is my car, then it is red. And then you could say, if the car is not red, then it is not my car. That's the contrapositive view of the direct approach. Okay? I don't have a red car, so there you can't conclude anything, right? The statement is true. Now, let's go to another proof technique. Induction. With induction, what we do is we prove the base case, which can be n equals 0 or n equal 1, typically. Then we assume that the relationship, this is usually when you have some value that you can iterate on. So now you assume true for the nth case, and that's called the induction hypothesis. Then you need to show that if it's true for the base case and for the nth case, then you need to show that it's true for the n plus first case. And that typically means that you're using the fact that it's true for the nth case. Let's just illustrate one of these one of these proof techniques for one of the propositions. Suppose we say, let's prove, or a proof of proposition 1.3 using contradiction. As a reminder, what was proposition 1.3? Proposition 1.3 said that every element or vector or object, every element in V has a unique additive inverse. Proof. First, let's just assume we have a vector space. So suppose V is our vector space. And now let V belong to the vector space. Let V be a vector in that vector space. Now, I'm probably doing more than what you'll normally see in somebody's proof. They may not even say this, but maybe they will. They might say by way of contradiction. They may not even say that. They may just say, suppose W and W prime are additive inverses. But now let me just say, preface that by way of contradiction. Suppose W and W prime are both additive inverses of our given vector V. Meaning now we are working from the fact, or we're making the assumption we are now assuming that W and W prime are different by that suppose statement. Suppose both W and W prime are additive inverses of V. So that now we have W is equal to W plus 0. We know that has to be true for our additive identity. But we can also now say that 0 is V plus W prime, since W prime was an additive inverse of V, which means that V plus W prime is the 0 vector. And now I can just be fast and loose with my associations. Let me just regroup these. But now W also was an additive inverse of V, so that now what's in parentheses is 0. But 0 plus W prime is now W prime, and that's our contradiction. We've now derived that W is equal to W prime, and we said they were different in our assumption. Therefore, W equaling W prime, that is a contradiction. Since we assumed W and W prime were different. Therefore, the additive inverse of any element of the vector space, little v element of the vector space, is in fact unique. And that's then a demonstration or a proof of proposition 1.3, and the proof technique we used was contradiction. Now, let's talk about the concept of subspace. We have vector spaces. Now, what can we sort of say about things that are maybe within that vector space? Can we have vector spaces within vector spaces? And the picture so here I'm trying to pictorially illustrate that U is a subspace of V. But how do we verify that U is a subspace of V? What properties does U have to have in order for it to be a subspace and not just a subset of V? Suppose U is a subset of V if U is also a vector space then we will call that set U, we will say then U is a subspace of V. And what I want to make very clear is that there is definitely a difference between a subset and a subspace. Note, there is a difference between a subset and a subspace. That is, every subset is not necessarily a subspace. In order to determine if U, where let's say is a subset of V, in order to determine if U is a subspace of V, we don't need to go through a lot of checks. We really just need to check three things. We only need to check three properties. And this is on page 13 of the second edition. And what are those three properties? One, we need this subset U to contain or have an additive identity. Or zero vector or zero element is in quotes. And you could see this then as if there's the zero vector in U, and that's a subset of V, it has to be the same zero vector in the big thing V. So the zero element in V is also in U. But you need U to contain the zero element. The second is you need, if you're in a subset U and you want that subset to be a subspace, it needs to be closed under addition. Whatever you've defined to be your addition property, so that if U and V are both in U, then you need their sum to be in U. And I think you can guess the third one. It needs to be closed under scalar multiplication. And those are the three things. You have to have a zero element, and it needs to be closed under addition and scalar multiplication. If you have A in the field, and U is a vector in your subset, then you need this scaled vector to also be in U. And the reason you only need to check those three is because the other vector space properties are really inherited from the parent, from V. The other vector space properties automatically or I should say the other vector space properties are automatically satisfied since U is a subset of V. And now you might just think about different subspaces. Let's say that you now, and maybe I will either try to collapse these down at the start of next lecture, but just think about what you're used to thinking of. If you now had a two-dimensional plane, what might be a subspace in that two-dimensional plane? A line, but what do you have to know about that line? It has to go through the origin, doesn't it? What's the smallest subspace you could have in this two-dimensional plane? The origin, the 0, 0 vector. What's the biggest subspace? Itself. So now in a two-dimensional plane, or in R2, you have these subspaces identified. The origin, lines through the origin, and the whole plane itself. Those are subspaces of R2. What about R3? You still have the origin, that's the smallest. You now have lines through the origin. Now you can have planes through the origin. Those are subspaces. And the whole thing. Those are subspaces. And you can start to think now about these more general vector spaces and what might be some subspaces in these more generalized vector spaces that we talked about at the start. So we'll pick up with subspaces and how we can combine those in appropriate ways next time. And check your D2L. I might give you a quiz to tell me whether you possess the second edition or the third edition. And the majority might determine where I pull the homework from.